Welcome to the debate. Today, we're diving into a really fundamental challenge in high-dimensional biology: how to strike that perfect balance between rigorous error control and, well, the need for actual biological discovery.
Our focus is the classic Golub et al. Data from 1999, looking at over 3,000 genes across 38 tumor patients.
Right, and the core of our debate today is a very specific choice made when applying a method called Significance Analysis of Microarrays, or SAM. This method requires you to set a threshold, this parameter called delta, to decide what's significant and what isn't.
Exactly. And the central question is this. Was the conservative choice the analysts made, setting that threshold delta at 1.11, based on the 90th percentile of the false discovery rate, was that the right call? I'm going to argue that yes, this highly conservative choice was a necessary safeguard for reliable, reproducible discovery.
And I'll be exploring whether that level of stringency is really justified here. I mean, is it statistical overkill that ends up just, needlessly shrinking our list of potentially critical gene markers? I think it sacrifices far too much power, especially given the limitations of the Golub sample itself.
My position really rests on the sheer scale of the problem here. We're running, over 3,000 hypothesis tests at the same time. So while the false discovery rate is the right tool to manage that, the potential for false positives is just massive. You have to be cautious. Subsequent lab validation of a false positive is incredibly costly in time, in money, and in scientific credibility. So the main goal has to be reliability. Sure, when we choose that 90th percentile, we're not just controlling the average FDR, we're demanding that in 9 out of 10 scenarios that the SAM permutation process might generate, the false discovery rate stays at or below 5%. This conservative selection of delta equals 1.11 ensures the list of genes we publish is truly robust.
Okay, I see the logic there. And I don't disagree that rigor is vital. However, by picking the 90th percentile, you're demanding an exceptionally high significance score. Let's just remember what delta actually is here. It's the threshold for the difference score, right? The test statistic that measures how much a gene's expression actually differs between the two groups. A delta of 1.11 is the minimum difference a gene has to show to be considered significant. Applying such a high bar has a huge impact on statistical power. We're analyzing only 38 samples, and they're split unevenly, 27 ALL versus just 11 AML. So isn't it reasonable to think that this kind of extreme conservatism is only appropriate if, a false positive is so much worse than a false negative?
In initial discovery research, especially research that becomes a benchmark for the field, the cost of a false positive does far outweigh the cost of a temporary false negative. I mean, if our list is contaminated with junk, every study built on it after that is at risk. That high delta threshold is simply a necessary filter to separate the real biological signal from the, frankly, significant noise in high-dimensional data.
Well, that brings us right to the quantitative impact of this choice. The trade-off between the 90th percentile and, say, using the median of the FDR distribution. If the median had given us a delta of, maybe 0.75 instead of 1.11, what are we really talking about in terms of the number of genes?
Well, the literature on this is pretty clear. The impact is substantial. If the analysts had chosen the less conservative median approach, they might have identified maybe 150 differentially expressed genes. By insisting on the 90th percentile at a delta of 1.11, they ended up with a much tighter list, perhaps only 50 genes.
Exactly. And that is my whole point. You're sacrificing 100 potential biological markers, 100 genes that showed a moderate but potentially real difference, all in the name of statistical purity. My concern is that while your list of 50 genes is statistically bulletproof, its utility is, it's restricted. What good is a perfectly rigorous list if it misses key drivers of the disease just because the dataset was too small to push their scores over that very high bar?
But maximizing information retrieval without controlling for reliability just leads to noise. With the median approach, you're accepting that half the time, the false discovery rate for your gene list is going to be above 5%. Choosing the 90th percentile is specifically designed to manage the instability in that permutation distribution. And for a data set with over 3,000 genes, that safeguard is essential. If the median were truly stable, why would the authors even call the 90th percentile the more conservative approach? It's an admission of how fragile the FDR estimate can be.
I'm not totally sold on that, because that fragility is made worse by the data itself. Let's focus on the sample size in that imbalance. 27 ALL versus only 11 AML samples. When you run permutations, the variance estimate for that different score is going to be heavily influenced by the smaller group.
And I'd argue those limitations make the conservative threshold more vital, not less. The difficulty in telling signal from noise in small, unbalanced samples means the statistical noise floor is high. That stringent delta of 1.11 acts as a filter against spurious findings driven by chance variability within those 11 AML samples. If we lower the bar, we just dramatically increase the probability that what we're seeing are artifacts.
That's a compelling argument, I'll give you that. But have you considered the consequence of what is effectively a double penalty? The small sample size already limits our power. Then you apply a stringent delta threshold on top of that, and it becomes nearly impossible for genes with genuine, moderate effect sizes to ever reach significance. We're risking a huge number of type 2 errors. It's highly probable that some of the most important genes are sitting just below that delta of 1.11 simply because they couldn't overcome the limited power of a 38 sample pool.
But the methodology itself, SAM, reinforces the rigor. It's a non-parametric method. It estimates the null distribution directly from the data through permutation, rather than relying on some assumed distribution. This data-driven approach lends a lot of credibility to the resulting delta threshold. By setting the threshold where 90% of the permutation variability is controlled, we're simply trusting the non-parametric estimate of the noise inherent in the Golub data.
I'm sorry, I just don't buy that. And let me tell you why. Yes, SAM is robust, but the stability of those permutation results depends critically on having enough ways to shuffle the labels, especially for that smaller group. When an analyst chooses the 90th percentile, it suggests a deep caution about the stability of the FDR estimate itself. If the estimate were truly stable, the median would be fine and would give you much more discovery. Choosing the 90th is almost an admission that the underlying distribution is highly variable, which is a known consequence of using these methods on small, unbalanced samples. They're choosing the safest path because the road itself is bumpy.
And that safety leads directly to the question of external validity. A list of 50 genes that is highly reliable, where we are confident the FDR is below 5%, is a list that is far more likely to be reproducible in an independent cohort. If we accept your expanded list of 150 genes, the higher accepted FDR would likely lead to poor replication in a new dataset. In the long run, the conservative list actually accelerates progress by providing reliable targets.
See, I would argue the opposite. The genes that barely clear your stringent bar might actually be the most fragile, context-dependent markers. Conversely, those 100 genes you're discarding might represent signals that were slightly weakened by technical noise in the original array, but are in fact strong biological drivers. By throwing them out, you ensure your list is reproducible, yes, but only because you filtered it down to the most obvious effects, potentially missing more subtle but critical genes. Are you really willing to accept that trade-off?
I am willing to accept that trade-off because the cost of rigorously validating 150 potential biomarkers, knowing many are likely false positives, is enormous. We have to consider the resource strain on the entire research community. By providing a tight, reliable list, we direct those precious resources toward targets that have already passed an exceptionally high statistical bar. It's an act of intellectual responsibility.
Responsibility, yes, but maybe not the most efficient exploration of the data we have. If we accept that trade-off, we have to admit the analysts prioritized minimizing downstream research costs over maximizing the information extracted from the original 38 samples. It becomes a decision based on resource management, not just statistical optimization for discovery.
So, to summarize my position, the decision to select delta equals 1.11 based on the 90th FDR quantile is, I believe, the scientifically sound choice here. It's a necessary defense against the instability inherent in permutation testing on small, unbalanced groups, and it prioritizes reliability and reproducibility. In short, quality over quantity provides the most utility in the long term.
And I'll conclude by saying that while that conservative approach beautifully minimizes the risk of type 1 errors, the resulting stringent delta value probably represents a missed opportunity. It highlights attention where statistical power was, I think, unnecessarily sacrificed for absolute stringency, potentially excluding numerous biologically relevant genes. The choice speaks more to caution than to optimal data utilization.
Ultimately, this discussion really reinforces that every single methodological choice in bioinformatics, right down to which quantile you select, has these profound and measurable downstream consequences.
Indeed, and it shows that optimization really depends on the research goal. Is the priority a bulletproof list for immediate clinical work, or is it a broader identification of targets for more foundational research? Thank you for exploring this with me.
A truly insightful exchange on the nature of statistical rigor. Thank you.